So first of all, like I said, this is something that is championed by Ariel Zhitnitsky, and this gentleman is a well-known theoretical physicist and with direct connection to axions, so direct that his Z appears in one of these unpronounceable model names, KFSZ. So what he says is the following, that so the theory of the, so that, I'm a plumber, and I'm talking about QCD now, so please forgive me for that. But so it's my impression of what he was explaining to me. So so basically the normal kind of matter that we have is just one possible solution, and in the early universe there could have been some other kind of state of the quark gluon matter that's called, I think, chiral quark condensate. Don't ask me too much about what this is. But then there was an idea that maybe part of that structure, which doesn't have nuclei, which just basically is a bag with quarks, if you want. These ideas were formulated by several people, including Witten and so on. But they all apparently had the problem that these things couldn't survive from the early universe to modern times. They were unstable. And so my understanding is that Zhitnitsky's contribution is that he proposed that chunks of this stuff are stabilized by this axion, the main wall, that's wrapped basically in a sphere, and that thing that holds this this matter together, and these things are stable. And according to Zhitnitsky, that this is actually all standard physics. The only beyond the standard model thing here is the axion, and we're all used to it by now. But the rest is pretty conventional. Modulo the fact that QCD is a non-perturbative theory, and it's really hard to make calculations of anything exact. So his theory is that some of these chunks survived, and he likes the certain size of these things. So the baryon number, or the number of quarks or antiquarks in these things is on the order of 10 to the 25, and these things are actually fairly large. He thinks they're on the order of 10 to minus 5 centimeter, and he thinks they are dark matter. Now, this thing is basically an antimatter ball. So if it hits the Earth, it explodes and deposits energy that's roughly equivalent to a small nuclear weapon. So yeah, you know what happened to the dark matter interacting very weakly. Well, first of all, it's actually not a problem for these anti-quark nuggets, because this energy of a nuclear bomb is not deposited locally. It goes as the anti-quarks annihilates, it goes through, and so it's basically a tube in which this energy is deposited the length of the whole Earth. So this interacts maximally strongly, right? But apparently, what astrophysics constrains is the ratio of mass and cross section, and these things have a favorable ratio of mass to cross section, and so therefore they nicely fit, according to Ariel, to both astrophysics, and also he finds evidence in experiments for this, things. To me, a little bit of a problem is that he, I think, is convinced that this is what dark matter is, and so he's quite confident that it is. And I think everybody should be very super skeptical always. I don't know. It's what can I say? That there are some ways to look for these things already in existing experiments. For instance, some of the limits come from IceCube, but some of these things, so some detection schemes can be done sort of motivated by the networks of sensors potentially, or by analysis of seismographs, for example. And Ariel found this kind of skyquake events and things that they are evidence. My personal preference is to like start with a model of these things and make predictions, not looking first at what is observed, and make a prediction for what kind of seismic, acoustic, and so on signals should happen. And that's what we've done here together. But there are some events that Ariel attributes to this. And then there are some people who actually take this a lot further. And there are, if you Google these anti-quark nuggets, there are many papers that discuss all kinds of consequences of these things. So that's another. This is this acoustic and seismic event. So that's basically currently the status of this thing. I don't know if that is satisfactory as a brief introduction to the topic.
I think one of the problems is also this quark nuggets are so complex. He seems to be able to explain almost anything with them, because they have so much phenomenology attached, apparently.
So they are flexible. For instance, going back to multiple elephants, they explain very naturally why you have the same amount of matter and antimatter. That fact, roughly, right? That fact actually comes. That explains it immediately. Interesting. All right. So
there's a raised hand.
Yeah. Raised hand.
Einar had a question.
Yes, please.
Can you hear me? Yes. I was just wondering again about this quark nugget. I mean, at what point does this form, and how does this work with the whole structure formation, CMB, and the baryon acoustic oscillations? I mean, you need dark matter to clump quite early, right, in order to get these oscillations.
So I can only say that I think Ariel has answers to these questions, and you need some stuff that has large ratio of mass to cross section, and that's what is important for astrophysics, including things like bullet cluster, for example, and then also about formation. But I cannot give you more detailed answer, I think. However, I think that Ariel Zhitnitsky is very happy to answer questions about this. So maybe you can just email him if you like. I'm sure he will. One thing I'm sure is he will have a good answer for you.
Okay, thanks.
Okay. Let's continue a little bit. And so maybe I say a few words more about this search for topological dark matter, and give you the example of our GNOME collaboration. This is Global Network for Optical Magnetometers for Exotic Physics Searches. And so this strange idea about correlating noise that I described to you currently turned into this pretty sizable collaboration of people who are doing very interesting things, including developing these advanced atomic sensors. And so our collaboration has a map, and it shows different stations in different places. It's all over the world at the moment. And here's a movie that was made by my colleague Arne Wickenbrock to illustrate. So I'd like to show this to you. So these are the stations that we have in different cities. I think this is the status of 2017. This is actually I want to say we took data. We have been taking data since then, but just now about to publish the results of the science run in 2017. So somehow don't underestimate the analysis. It takes much longer than doing the actual experiment to do it properly, as we found the hard way. Anyway, so here are all of these magnetometers in different places. And it is important that the Earth, the whole solar system, is actually moving with about 10 to minus 3 again of the speed of light in a particular direction towards the Cygnus. Yeah. And so that would be the sort of preferred, not necessarily the orientation where the dark matter is coming from, but the preferred direction. And so these devices are insensitive to real fields, but sensitive to gradients. And so there is a direction of sensitivity. And so the dark matter wall comes through this axion, the main wall. It should create a sequence of events with a characteristic timing of maybe half a minute or something, because the speed is 10 to minus 3 of the speed of light, so it's not so fast. And so then what we do is we constantly monitor the signals from the network. And did it just stop? Okay, I thought it should go further, but anyway, and then we have sort of these events, and we run a computer analysis to determine whether the event that we see is consistent with a particular direction and velocity of the wall and the strength of interaction. And from that, we can constrain abundance. We have been looking. So far, we haven't found dark matter. So otherwise, you would have already heard about it. But it's we feel it's a very cool way to search for dark matter. And now, as this experiment matures, there are more and more sort of science scenarios that are being developed to use this for different cases, including, for instance, non-topological dark matter currently, and also to search for exotic particles that or fields that may be originating from some catastrophic, so to say, events in the universe, like black hole mergers or things like that. Oh, why is it again showing? I guess it's just repeating. Sorry. Okay. Yeah. So, like I said, that analysis is something we underestimated in the beginning, and in fact, maybe it would be interesting for you. We took a wrong strategy. We thought that the problem of correlating remote sensors had been solved by LIGO, And we in fact had a person from LIGO as part of our collaboration who at first trying to set up this analysis. And moreover, it turned out that LIGO has open libraries that you can download and use. But what we didn't appreciate is that you know, the people who wrote some of those libraries were no longer with the collaboration, and the later versions didn't match the, you know, some parts didn't match the others, and so basically after quite a while of trying to rely on these things and improve them, we actually did absolutely everything from scratch, and this took us a bit of time. But now we're very excited. This paper just came back from reviews, and the reviews are very enthusiastic. So this should appear in, I believe, Nature Physics, hopefully. It has not been accepted yet, but very, very close to it, I believe. All right. So just to continue to give you a feeling for how people look for dark matter, let me tell you about the work that my colleagues, another set of, I have many colleagues everywhere actually, but even within the University of Science and Technology, I have lots of friends and colleagues. So this is one group. This is a group led by young Professor Jing Rong and senior Professor Zhangfeng Du. And these guys are doing indirect search for dark matter. This is this type, remember, where it's not the galactic dark matter, it's the modification of the interactions between particles due to virtual potential dark matter candidates. And what they use is this very popular platform these days, is these nitrogen vacancy color centers in diamond, of all things. And these things are very attractive because these are basically sensitive magnetometers and also nanoscale magnetometers. So they allow, in principle, go down to atomic size. And here it's sort of a micro scale, not nanoscale, but still an interesting one. And they have a test mass, for example, attached to a tuning force, and they wiggle it near the spin, and then they see if this test mass affects the spin due to these exotic interactions. And I must say that this business of doing new physics with this fifth force type exotic interactions, it has a long history. I think one of the pioneers was Frank Wilczek, the same guy who gave the name to the Axion, Nobel Prize winner and very smart person. And he made the first rough catalog of these interactions. The catalog was further refined by Dobresko and Moschow several years back. But when we started also looking at this, we found that there are still some deficiencies in that exotic interaction catalog. And so there is a new one now that relatively new that was done mostly by the work of these two talented young people, Pavel Fadeev and Philip Fichik, and with the able help from Evgeny Stadnik, and led by Mikhail Kozlov and Victor Flambaum. So it's a new catalog that I recommend, and these are the older ones. And yeah, anyway, back to this Chinese experiment with nitrogen vacancy centers. So if you look at these catalogs for exotic interactions, you see all kinds of things, starting from the basically just Yukawa force that's spin independent, for example. There are also spin dependent interactions and what's called monopole. Dipole is mass affecting spin, and spin, and there are parity violating and parity conserving. And so this group was looking at different things and putting nice new limits on a particular interaction range, which is the inverse mass of the exotic particle. And here we're talking about some micrometers, tens of micrometers. And the funny thing is that last year, these guys have actually found 2 axions according according to them. You can look in this preprint. I hear, I'm not sure what the current status is. I hear there's possibly some systematic that they have found, but I don't know yet. I actually wrote to them an email to ask about the very latest, but in principle, this paper on the archive is reporting some exotic things. But one shouldn't get too excited yet about this, but it's just to show that this is a very nice way to look for this possibly dark matter related physics. Yeah, so I also mentioned to you about the levitating magnets, and maybe I'll tell you a few words about that. So it goes back actually to a problem for students that we came up with for our, we have an atomic physics textbook with Derek Kimball, my former student, and David DeMille. Yeah, and there we decided to ask a question. So if you put if you put a compass needle at an angle to a magnetic field and you let it go, the needle will be oscillating around the magnetic field. If you take a spin with a magnetic moment and you prepare it at an angle to magnetic field and let it go, it does something completely different. It undergoes Larmor precession. And the question is, what's different between, what's different? That's the book where the problem is. What's different between these things? And you realize that actually what's different is that when a compass needle moves, there is this motion of this solid body as a whole, and there is an angular momentum associated with that motion. But if you start thinking about it, then if you like prepare a magnet at rest, there are a lot of electronic spins in a ferromagnet, basically 1 h-bar of angular momentum per atom. This is a sizable angular momentum, and there is a regime where this angular momentum actually dominates over this mechanical angular momentum. And we immediately make a prediction that if you put such a needle in a very weak magnetic field, it will precess like an atom with basically with the same Larmor frequency. And then you ask the next question is about what if you say you want to make a magnetometer out of this. So you just put this magnet and you see how it precesses, and then you measure its precession, and we started analyzing the sensitivity, and to our great astonishment, we found that it seemed to be beating the standard quantum limit, assuming that we have the same number of spins and we do independent measurements on them. And so we were completely stunned by this, and it took us a while to understand how this works. I'm not going to go too much into detail, but it has to do with the sort of peculiar properties of a ferromagnet, where you have all of these spins pointing in one and the same direction. And so the relaxation time for spin projection along that direction is actually infinite. But if you get the spins to sort of deviate from that direction, there is a very fast damping. So it's a highly anisotropic system. And what it does, it actually takes the noise, the quantum noise that is inevitable quantum noise, and it pushes it towards higher frequencies where we're not measuring. And so this allows you to basically do very nice measurements, we believe. And so this is one system we are also proposing to use for measuring these exotic interactions. For example, this particular fairly complicated fifth force type potential, and we project, we haven't done this yet. We are kind of working on experimental realization of this magnet that is freely suspended. That turns out to be very tricky experimentally. But if we succeed, that should be a very powerful tool to limit this kind of interaction. But just to make a little comment here, if you allow sort of your imagination to float even further, you can launch these things into space. And if you do, then you can do an experiment that we call gravity probe spin, in analogy with gravity probe B, to look for general relativity effects on the spin, and to ask and answer a very simple and a very basic question. So so we know that how basically general relativity effects work on a classical spin. That was the gravity probe B experiment, which basically launched mechanical gyroscopes and detected these relativistic effects. And the question is, if you are now talking about quantum spin, yeah, or electron spin, will this spin respond in the same way? And if you ask me to bet, I would say probably yes. But this is something that is one of the main questions in modern physics, is how to marry general relativity and quantum mechanics. And so this is a very interesting thing to ask, and that's what we are proposing to do. Yeah, so these kind of potentials, exotic potentials, offers you a very interesting, sneaky way to search for exotic particles, potentially dark matter particles, and this is a kind of physics that I call couch physics. Why is it couch physics? Because you do not do a new experiment, and you don't do any complicated theory. So you rely on the fact that some people work very hard, and in this case, for instance, do helium spectroscopy and measure transition energies in helium, which is a fairly simple atom with many digits. So now you have a catalog of exotic interactions. These are the exotic potentials. And for helium, for example, you have also tabulated wave functions, atomic wave functions. So what you can do is you can ask your summer undergraduate student. So Philip Fitchik was such as a student some years ago. Now he's about to graduate from the Jagiellonian University, and so he did this beautiful work where he took these wave functions from Beta Salpeter book. He took the potentials and he did the integrals, and he calculated how much these energies should be shifted. From what? From also theoretical calculation, typically done by some other professionals like Krzysztof Pakucki and others. And so now you mostly there is an agreement for helium between theory and experiment, and now you compare what you predict from the effect of the exotic potential with the difference between theory and experiment, and you put very nice limits on all of these exotic potentials. So that's what we've done for helium fine structure using fine structure spectroscopy, and it turned out to be for many parameters superior limits than came from other experiments. And later on, we also extended this to actually something much more exciting even. It is an exotic atom called antiprotonic helium, which consists of a helium nucleus, helium-4 nucleus, and an electron. And instead of the second electron, you have, excuse me, you have an antiproton. So in this work, we were able to set actually direct experimental limits on what's called semi-leptonic interactions of antiproton with electron. And it was still couch physics largely, even though more involved than helium. But yeah, so that was a pretty exciting way to go. Now, in the meantime, there are other examples of these approaches. Also, the same idea: look for exotic interactions. And there is one proposal that originally was formulated by a good friend of mine, Professor Gilad Perez from the Weizmann Institute, and it was interesting because the whole world tried to sync Gilad's idea. You know, like I was at several meetings where like everybody was really attacking him, that as a big professionals, you know, and they were explaining how he's wrong. And he was there was a bit of a problem with the way he formulated his idea at the you know, on the first pass. But there was a beautiful core of this idea, and eventually it was possible that very few people came to his rescue, and some of them are actually, some of the people here, I'm not going to name names on this list of co-authors, were trying to sync his idea, and then we won them over, and they became supporters of this idea. And now this is actually
Dima, could you remind us? I think the original proposal was actually to look for the Higgs boson, but then there is the electron-Yukawa coupling, which is tiny, and the Higgs boson is point-like. Wasn't that the issue? Or?
Yeah, that was an issue, yes. But that was a previous paper. So this one, so that's why I'm showing this paper. And this was when that formulation was amended. And so this one is now correct, I believe. And it's one of the hottest things now in atomic spectroscopy. And I'm going to say a few words about this for you. So this has this effect called the isotope shift. And now I'm so happy because, you know, I graduated from the university in Novosibirsk in Russia in 1985, and I did my diploma thesis in 1983, so quite a few years ago, when most of the audience wasn't born yet. And I did my diploma on spectroscopy of samarium, and now I have a chance to show you the data from my diploma, you know, to explain this. I'm very excited about this. Anyway, if you look at the optical spectra, for example, of some atom, and in this case we have samarium, and you have a spectral line. If you have good resolution, fine resolution for it, you see that the line is actually, it has a complicated structure. It has many different peaks, and if you analyze this, you realize that these are different isotopes. These are stable isotopes of samarium, and they have slightly different energies. Okay, and you might wonder why. Well, first of all, the configuration of this transition is so you have xenon with all closed shells, and on top of xenon you have partially filled 4f shells with 6 electrons here, and then another closed shell 6s square on top of that. And this particular transition is when one of these s electron goes to p electrons, and you see this is frequency, and yeah, and you see that here you have what's called, what happened? Here you have what's called a negative isotope shift. So the heavier the isotope, the smaller the transition frequency is. And then you can look at another type of atomic transition. And here, this 6s shell remains intact, unchanged, but you have one of these 4f electrons is promoted to 5d. And you make a recording of the spectrum, and you look at it, and you might think, you know, you're going crazy, right? Because this picture, that's what I thought when I first saw it in my diploma, because you see this picture, and then you see basically a mirror image of it. So you have same size, but positive shift. You see, a heavier isotope now has higher energy, and here it has low energy. Okay, and it turns out that this is what you actually expect, because the isotope shift has a different. So why is that the energy is slightly different for different isotopes? So one is that what enters the atomic energy is a reduced mass, and you have the what's called the mass shift. Is because different isotopes correspond to different reduced electron nuclear mass. Then there is another effect called anomalous mass shift, and that has to do with the effect that sometimes electrons move in correlated ways, and that may enhance the effect. But in these heavy atoms, the main effect comes from the fact that the nucleus is not a point. It actually has a finite size, and so you have a deviation from the Coulomb potential near the nucleus. And so there is something that's called a field shift, and it depends on the density of electrons at the nucleus. If you remember your atomic physics, it's only s electrons have finite density, and so then you can immediately understand why you have negative shift. Is because here you have two 6s electrons, and here one is promoted to 6p, so you have only one left. The density on the nucleus drops, you have negative shift. If you look at this configuration, you're puzzled at first because the number of s electrons is the same, but it turns out that there is a shielding effect of this 4f shell, which is very compact, as it turns out, in atoms, and it shields the s electrons partially. And when you perturb this shell, the shielding coefficient changes. It's not shielding so efficiently, so the density of 6s electrons actually increases, and that leads to the positive shift. So it's fun for a diploma, I guess, but the point is that you can do an analysis of spectra in different transitions and for different isotopes. And the idea is that you plot the isotope shifts in one spectral line versus the isotope shift in another spectral line for different pairs of isotopes. And if you have some simple assumptions about how this works, that you know, the isotope shift is basically a combination of mass and field shift, and that the field shift, for example, depends on an atomic factor and a nuclear factor. So there's very simple factorization that tells you that if you do this, you should get straight lines. So the idea that Gilad had, and that was later refined in this paper, is that you can actually look for deviations of nonlinearity in these King plots. And this would be a fairly model-independent way of looking for new physics, which is particularly sensitive sort of for relatively light bosons. And I must say that after this, in the last few years, there are a lot of groups that are doing precision spectroscopy that are starting to do this, and in fact, observing this nonlinear shift. Now, there are subtle effects that are not due to exotic physics that can also produce nonlinearity. And now there is a lot of work on trying to understand these and see if there is new physics or not. And I must say that our group is also in these guys involved in this kind of activity, and we are collaborating with theorists here and about to submit a paper that describes measurement of isotope shifts in 2 photon transitions in ytterbium. This is very interesting because a group of our colleague Vladan Vuletic at MIT has in fact measured already isotope shifts at the same level as us, but now not in a neutral ytterbium, but in a ytterbium ion. And this comparison, the King plot, should be very interesting. And so we are very excited. I'm not ready. We do have it, but we're still verifying it. I'm not ready to show you, but this is something that's very, very hot at the moment. Yeah, and so these were some of the things. I just want to show you this because it's not all talk. There are references for a lot of things, and some are published, some are on the archive, but there is actually something to read about every item here, so if you like. All right. That was actually what I was planning, honestly speaking, for my first part. But I'm glad. I'm very glad how it is going because we are discussing a lot of things. But the second part was supposed to be to dig in a little bit deeper and back to axions. As Andreas said, the name. It sounds scientific, like pion, muon, axion, but it's actually named after the cleaning solution. And yeah, Wilczek said in his Nobel lecture that he named it after the axion because it was supposed to clean up a major problem, which is a strong CP problem. Okay, we can skip this, we discussed this. But now we come to something to repeat what Andreas mentioned here already is, if we want to look for this axion or axion-like particle, how do we do it? So, well, we assume that it interacts by gravity to have the nice dark matter effects, but what else? And as Andreas said, there are not so many possibilities there, right? So, for instance, one of the possibility is interaction of the axion with photons, with electromagnetic field. So let me just show you what we have here. So this is electromagnetic field tensor, F mu. This is the decay constant, the parameter basically that Andreas was talking about. And A here is the amplitude of the field, of the classical field corresponding to these many axions in a mode, if you want, right? So we are going to be describing this with this field A. So this photon interaction, it's a basis of most experiments actually, and I think I would say until 2014 when we started CASPAR, I think this was the only interaction that was used. Andreas will correct me, but I believe that's the case. It was the only interaction that was used to search for axions. And then in about 2013, Peter Graham and Surjit Rajendran at Stanford, they pointed out to these other types of interactions, say, guys, why don't we use them? And the next one, which looks just like the photon interaction, only you you replace the electromagnetic field tensor with gluon tensor. So photons are replaced with gluons. Okay, and so this interaction it leads to an electric dipole moment. So basically this creates this theta term, and as Andreas said, the electric dipole moment of a nucleon is proportional to this. If the field is oscillating, then you will get an oscillating electric dipole moment. And so our Caspar electric is searching for this, but in the meantime, also the PSI, Paul Scherrer Institute neutron electric dipole experiment reanalyzed their data to look for oscillations, and they have beautiful limits at the very slow, at the very low mass range. Now, the third and final interaction is, as mentioned by Andreas, the gradient interaction. So what do we have here is, instead of the axion field, we actually have this 4 gradient of, right? So d mu times a derivative. And this is a fermion current, and this like I don't know, if you don't write such Lagrangians every day, that might look scary, but in fact this is a beautiful thing, because if you take non-relativistic limit of this becomes just the spin. This is proportional to the sigma matrix for say neutron or proton. And this reduces to just spatial gradient. Now, axion field, remember, is a pseudoscalar. So a gradient of a pseudoscalar is a pseudo vector. And a quiz, what pseudo vectors do you know? And right, you thought correctly of the magnetic field. So what we have here is magnetic field times spin. So it's B dot S. So this is basically the Zeeman interaction with this quasi-magnetic field produced by the gradient of the axion. And if this object oscillates here, then you have an oscillating magnetic field. And that's the idea in the Caspar gradient experiment, formerly known as Caspar wind. Now we don't call it that way. Also the GNOME, the network I told you about, and also some other experiments. For example, a really beautiful experiment in Italy called Quarks. This sounds like a duck, but in fact it comes, I think, from the Latin words quore axione or something like that, looking for axion. The key ideas behind this experiment that will end up looking very much like an NMR nuclear magnetic resonance experiment is that dark matter could be this kind of a classical field that ignores shielding. It oscillates at the frequency proportional to the mass of the underlying particle, also known as Compton frequency. It has a relatively narrow line. In the standard halo model, we discussed this Q factor is 10 to the 6, so delta nu over nu is 10 to minus 6. There is interaction with spin, so we come to the cosmic, because it's actually a haloscope, cosmic axion spin precession experiment, or Caspar. So now again, there are 2 new interactions that we are looking for, either this gluon interaction that causes oscillating dipole moment, and the Hamiltonian here, that effective Hamiltonian that will be used is that, so there's the spin and it interacts with a static electric field because it's a dipole moment interaction. And in the Caspar gradient, we don't need any fields. It's just already effectively a magnetic field that's proportional to this gradient of the axion field. Then, how does a nuclear magnetic resonance experiment look? We create some nuclei that we orient along some external field, and in Caspar electric, we apply a strong static field perpendicular to the spins, and dark matter induces the dipole moment along the spin, and there is a torque that causes effectively spin precession, taking it out of away from the direction of the magnetic field. And in the gradient experiment, this torque is provided by this quasi-magnetic field of the axion. Then, if this happens, we get the spins, nuclear spins precessing around magnetic field, and we can pick it up with a coil or a squid magnetometer. And this is the principle of the experiment. Now, the fact that in one case we need to apply electric field, in another we don't, leads to rather different optimization of the experiment. And so Caspar electric is in Boston, and it's led by Alexander Sushkov, Professor Alexander Sushkov. I'm super proud because he's also my former PhD student, graduated from Berkeley some years ago. And here, what we have is, so this is basically an NMR system that goes into a magnetic field, NMR magnet, and the sample here is a ferroelectric material that has strong electric field always present. And then we do NMR and look for this. We change the resonant frequency, and this process of tilting the spin away from the axis is actually resonant. This happens most strongly. It happens most strongly when when the Larmor precession frequency is resonant with the Compton frequency, with the frequency of the oscillation of the field. And so looking for axion involves scanning this magnetic field. All right, so okay, so we are in the beginning of the road here. So this is our result, and then there are many projections. And I'm not going to bore you with what we're going to do, but you can see that we are going to go definitely beyond the supernova limits, one thing, and moreover, with some work, within a few years, we hope to reach this line, which is basically the most strongly theoretically motivated line where this QCD axion sits. And for these electric experiments, we actually expect to reach that line. This is very important because Andreas mentioned briefly in his talk is that here, this is the Alp area, and it's kind of hard theoretically to although not impossible, and Andreas' recent work showed how to do this, okay? But it's a bit hard to populate this region, but this would be sort of your classical vanilla QCD axion, and this would be a very nice, milestone. So sometimes people who are critical of this whole dark matter search field, they are saying, well, okay, you look for something and you maybe will not find, but you can always say, okay, I'm gonna go 10 times more sensitive. And then if you don't find anything next year, you say, I'm gonna go 10 times more sensitive. And then you can spend all your life looking for nothing. But it seems to me that in the case of axions, this is actually not the case because there is a well-defined boundary. So once you cover this parameter space with a number of experiments, that basically reaches to the QCD line, then you can maybe say, okay, well, there is no axion in the okay, with this frequency where you measured, and that would be it potentially. Okay, so there are, coming to what's going on in MINDS. In MINDS, we started working on the gradient experiment, and while we were doing this, we realized that an experiment that was completely independently or for completely different reasons going on next door to the Casper experiment actually could be converted as a fun, quick experiment for looking for also dark matter in the very low frequency range. And this has to do with something called zero field NMR. This is quite an unusual way to do nuclear magnetic resonance, because normally people like to have bigger and bigger magnets. Instead of magnets, we have in our experiments magnetic shielding, actually, and that's where we do the experiments. And the idea is that if you turn off all the fields, then the normally very feeble interactions, such as the ones, for example, between the nuclear spin of carbon-13, it's a spin 1/2 nucleus, and the proton, the so-called indirect spin-spin couplings, they become important. And so this system forms, is now described by the total angular momentum of the two nuclei, and these are two spin 1/2 nuclei, so you can have F equal to 1 and F equal to 0. And if you excite a coherence here, these resonances, they have pretty long relaxation times, tens of seconds, and you get narrow lines that we detect actually with atomic magnetometers. So we decided that why not use this for search for dark matter. And briefly, maybe I'm not going to go into great detail here, but just say a few things. So that if you don't have any external field, you have this single resonance. If you apply a bit of magnetic field here, you split the resonance. And if in addition to that, you modulate this field, you acquire some kind of sidebands in your signals. So now what you can do is you can say, okay, let me turn off my field modulation, but let the axions in the galaxy that are here also in our lab do the modulation due to their quasi-magnetic field, and then we will look for sidebands. And we did this kind of experiment, and there is a little problem that you encounter, is that I showed you that the coherence time of the measurement is about 10 seconds, but the coherence of the axion is expected to be maybe about a month or so for this range of frequencies we looked at. And the question is, can you take advantage of this? And it turns out that yes, by doing repeated experiments with careful timing, then you have a problem that you don't really know the phase of the exotic field. And so the question is, how do you make averaging? And so here we use something that we learned doing spectroscopy of nitrogen vacancy centers. It's something that's a technique called coherent averaging, and it takes advantage of computers being powerful, so you can basically add things with different phases and see if for one particular phase you have nice signals. And this all worked brilliantly, and we got nice limits on dark matter at correspondingly some frequency range, I don't know, 10 to 100 hertz, that kind of thing. Then we got a bit ambitious, and we said, why don't we try to look for this dark matter closer to this 10 to minus 22 limit, very, very slow oscillations. And here you run into a bit of a problem, because how do you distinguish the exotic magnetic field of very slow and tiny drifts of magnetic field in your shield that happens over a long time. And here we had an idea that I'm kind of proud of using comagnetometry. Let me explain how this works. So there are in general in molecules you have several groups of lines, not one but several groups of lines, and these lines, if you calculate how they are sensitive to magnetic drifts and how they are sensitive to exotic physics, is a bit different. And so comparing them in one and the same molecule, you can take out the drift and separate the exotic physics. And we implemented this and tested that the actual magnetic drifts are strongly suppressed, worked very well. And then we used this to actually look at dark matter, and we were very happy with the results. So the first result, first technique with sidebands, it was this kind of range of frequencies, and the other comagnetometer part was here. And here was actually the place where we ran into this trouble with incorrectly accounting for this stochastic nature of dark matter initially, and then we corrected this. And then there was also this neutron. Actually, the neutron EDM guys were slightly ahead of us, but we were exploring these regions here. So on the one hand, you can say this is kind of not so meaningful because there is a supernova limit, but there are a few things to say. First of all, while we were doing this, there was severe discussion in the literature about how seriously you have to take the supernova energy loss model. And so there was a few orders of magnitude disputed parameter space. That's one thing. And the other thing, we were very excited because we used NMR here with thermal polarization in the magnet, but nowadays in our laboratory we have techniques for what's called hyperpolarization, much higher degree of nuclear polarization, and so we projected the results here, and I'll tell you what happened to them. But it was a lot of fun. Okay, and what happened was that there appeared some competing techniques around this range. First of all, theoretical analysis and also experiment by a group in Israel. This is an experiment that's called NASDUK, and it's on the archive at the moment. And also, this experiment is by my colleagues at the University of Science and Technology, and I'll show you where they are, but in a minute. But before that, in the meantime, the actual CASPER for higher frequencies is being put together, and we split it also into two field ranges for technical reasons. So this is CASPER low field. This is 0.15 Tesla superconducting magnet. I call it the world's lowest field superconducting magnet, but we still decided to go to superconducting for technical reasons again. And we are about to get, we are very excited, a stronger magnet that will go to 14 Tesla, and with xenon, which is the material we want to use, allow us to go to 166 megahertz, and using protons perhaps 4 times higher frequency. And so these are these projection plots for different things. And okay, the general structure you are probably already used to this. This is the Alp mass here in electron volts. This is the frequency, and this is the coupling constant here. Right. So this is the USTC experiment. It's for very low frequencies, and this is using some kind of a atomic device that in this case is called a spin amplifier. It's a vapor cell that contains xenon atoms and rubidium atoms. And rubidium atoms, they serve multiple purposes. First of all, you do optical pumping of rubidium. You polarize them, and the rubidium atoms in collisions with xenon, they polarize. They polarize the xenon nuclei. Then these xenon nuclei are sensitive to the quasi-magnetic field produced by ALPS, and they undergo precession. And rubidium atoms again collide with xenon and are used now as a magnetometer to read out the precession of xenon. This is in a way a transducer between this exotic field and actually the field that is read out by rubidium. So these experiments have done
I'm going to briefly interrupt you. We should just make sure to slowly come to an end. To maybe we can then shift the further discussion to the exercise.
Yeah. How many minutes? How many minutes?
So we are already 10 minutes late, but you can continue for some minutes, and then we shift to the next
Sorry
session.
about that. I got. Give me like a couple of minutes to get to a nice stopping intermediate point.
Perfect.
On wisdom. All right. So I just want to say that these experiments have done pretty well, because this was our Kasper-Zulf, and now this is, you know, several orders of magnitude better. That's where we are. Yeah, I'm glad I'm a co-author on this paper. Okay, let's see. Yeah, so these are the fifth force searches that I mentioned that can be done with the same apparatus. Also pretty nice. And also there are ways to configure essentially the same basic device as a self-oscillating magnetometer, or you can call it a Floquet maser, and it's a wonderful nonlinear system with all kinds of tricks you can play, also sensitive to dark matter. So it's a lot of fun. And this is Jiang Min, who spent some time as an undergraduate student and then a graduate student both at Berkeley and Mainz in our lab, and then now he's assistant professor at USTC, and this is a graduate student, Haowen Su. All right, let me just stop here. This is about stochastic fluctuations. So this is a very good place to stop. So just in summary, I guess in the first part we talked about some general picture of ultralight bosonic dark matter and some other things like alternatives to it and how it fits in the general picture. And we started the second hour by looking at one of these alternatives, which is axion quark nugget model, and then we dug in a little bit to talk in some level of detail about the NMR searches for dark matter. So thank you very much for your attention, and I think we have some stuff to talk about during the discussion.